February 22nd, 1943. Portland, Oregon. The river mist hangs low over the Kaiser shipyard, thick enough to taste. Sparks from welding torches dance in the gloom like fireflies, flickering across the hull of a half-finished Liberty ship. Floodlights throw long shadows of men in heavy coats and masks, their silhouettes swallowed by fog and steel. The SS John P. Gaines has just returned from her trial run. A sturdy new vessel, 431 feet of American steel and urgency. Workers swarm her decks, checking seams and hatches before the next convoy east. She was meant to be one of thousands, built not for beauty, but survival. The war has no patience for elegance. Then it happens. A deep, low groan, the kind that makes every man freeze. Metal straining against itself, a sound like thunder rolling underwater. A welder drops his torch. What the hell? The ship cracks. A seam along her midsection bursts open with a deafening boom, splitting her nearly in half. The deck heaves upward, plates peel apart like bark from a tree. Men dive for cover as the hull ruptures, water rushing in with terrifying speed. In seconds, the Gaines is sinking, not from enemy fire, not from storm or collision, but from within. When the smoke and spray settle, the docks are silent. The shipyard foreman, still shaking, mutters, "She broke herself." Word spreads quickly. It isn't the first. Across both oceans, Liberty ships, the very backbone of the Allied supply line, are cracking apart. Some at sea, some in port, some while moored quietly at dock, entire hulls snapping like glass. At first, investigators blame the welders. Too rushed, too careless. The new welding method, faster than old-fashioned riveting, had been hailed as the savior of wartime shipbuilding. But now it looks like a curse. By March, the U.S. Maritime Commission is panicking. "We've lost ships to torpedoes, yes," one official says bitterly, "but never to the cold." It's the cold. That's the whisper among engineers. Ships that survive the tropics are dying in northern waters. Steel that should bend under pressure is shattering instead, cleanly, completely. Something inside the metal is wrong. And halfway across the Atlantic, in a small laboratory under blackout conditions, a British scientist named Dr. Constance Tipper is about to prove it. March 1943, University of Cambridge, England. The city lies in near darkness, its spires barely visible through the fog. Outside, sirens wail distantly, another air raid somewhere near London. But inside the metallurgy department, only one sound matters. The ping of breaking steel. Dr. Constance Tipper leans over a test rig the size of a sewing machine, her glasses fogged slightly from the heat of the lab lamp. She's in her 50s, with a sharp gaze that can cut through excuses faster than any torch. On the table before her lies a small, notched strip of Liberty ship steel, cooled to near freezing. Her assistant, a young student in a wool sweater, braces as she lowers the lever. Crack. The sample snaps clean in two. No bending, no deformation. Just sudden, perfect fracture. Tipper exhales slowly. "Again," she says. The assistant slides in another piece, this one warmed over a burner to mimic tropical conditions. The lever drops. The steel bends like soft clay. She straightens, adjusting her spectacles. "Temperature," she murmurs. "It isn't fatigue. It's transition." For months, engineers across the Allied world have been chasing ghosts, blaming welders, blaming design, even blaming sabotage. But Tipper, a Cambridge metallurgist who spent her life studying the subtleties of how metals fail, suspects something far simpler and far more dangerous. At low temperatures, ordinary steel undergoes a transformation. It stops being ductile, able to stretch and yield, and becomes brittle, like glass. Once it reaches that point, a single flaw, a hairline crack, a weld under stress, even the vibration of a hammer, can trigger disaster. She notes in her ledger, steel's capacity to absorb energy collapses below a critical threshold. Brittle fracture may propagate faster than the speed of sound. The Liberty ships, built in haste with low-toughness steel, are sailing through Arctic winds and sub-zero seas. The perfect conditions for catastrophe. Tipper's findings will soon be tested in full. 2 days later, her lab receives crates marked Property of U.S. Maritime Commission. Inside are fractured hull plates from the doomed John P. Gaines, her steel bent, torn, and split. The telegram accompanying it reads, "Urgent, determine cause of failure. Stop the dying ships." Tipper spends nights in the lab, her breath fogging in the cold as she compares samples under magnification. The weld lines gleam under the microscope like frozen rivers. There, a notch, invisible to the naked eye. And there, crystalline fractures, sharp and angular, running clean through. She looks up, jaw tightening. "It's not bad welding," she says aloud to no one. "It's bad steel, frozen to death." Within weeks, she devises a simple, elegant diagnostic. A small-scale bending test, performed at various temperatures to reveal whether a metal will flex or fracture. It's fast, conclusive, and unambiguous, the kind of test even a shipyard can perform. They'll call it the Tipper test. In one of her reports to the Admiralty, she writes, "We must stop blaming the craftsman. The failure is not human, it is metallurgical." Her discovery will not only save ships, it will expose a blind spot in the industrial rush of total war. That speed without understanding can be as deadly as any enemy. By the summer of 1943, word of her test begins spreading quietly through shipyards from Glasgow to Baltimore. The Liberty fleet, once feared Kersad, may yet be saved. If the world listens to a woman who can hear steel speak. June 1943, Baltimore, Maryland. The harbor smells of diesel, salt, and steel dust. Riveters hammer along the hulls of Liberty ships in unison, a chorus of clangs echoing between cranes. In Dock 3, the SS Samuel Chase stands half-finished. Another in the endless line of cargo vessels meant to feed the war machine across the Atlantic. But this morning, something is different. A small group gathers near the bow. Engineers, naval inspectors, and foremen in rolled sleeves and hard hats. Among them is Dr. Constance Tipper, her gray coat buttoned tight against the humid air. She has crossed the ocean under military escort to demonstrate her method firsthand. The Americans have heard the rumors of ships snapping mid-ocean, of cargo lost without a shot fired, and of a woman in Cambridge who claims she can stop it. The foreman, a burly man named Al Greer, wipes sweat from his neck. "Ma'am, with all due respect," he says, "these ships are made the same way every time. Same steel, same welders, same process. We don't see what could be wrong." Tipper kneels beside a test rig mounted near the hull. A small steel bar, cut from the Samuel Chase's plating, rests between two clamps. She nods to a technician, who lowers the temperature using dry ice. The crowd watches in silence. With one sharp pull of the lever, crack. The bar splits instantly. The sound is small but shocking, like glass breaking in a church. Tipper says nothing at first. She simply hands Greer the fractured piece. "Now try one at normal temperature," she instructs. The lever drops again. This time, the steel bends. No break. She stands, brushing her hands on her coat. "Gentlemen," she says quietly, "that's the difference between a ship that lives and one that dies." The engineers stare at the sample in disbelief. The evidence is undeniable. The same steel that holds firm in summer will shatter like porcelain in the chill of the North Atlantic. Over the next days, Tipper's team performs dozens of tests. Some of the steel, from mills in the American Midwest, shows alarming brittleness. The culprit lies not in design or welding skill, but in metallurgy. Too much carbon, too little manganese, and impurities that make the metal crystalline under cold stress. The results are wired to Washington within hours. The Navy and Maritime Commission issue immediate orders, stricter steel composition standards, mandatory low-temperature tests for all new hull plates, and emergency retrofits for ships operating in Arctic waters. One evening, Tipper walks the length of the dry dock as the sun sets over the Chesapeake. The air smells faintly of hot oil and salt spray. A welder nearby removes his mask and nods to her. "Mom," he says with a grin, "they say your trick's saving our ships." She smiles faintly. "It's not a trick," she replies. "It's just listening to what the metal's been trying to tell us." Within months, the number of Liberty ship fractures plummets. Hulls, once doomed to crack under the stress of icy seas, now endure the worst conditions the Atlantic can offer. Convoys begin to cross safely again, each one carrying fuel, food, and hope to a starving Europe. The Allies don't celebrate it openly. Secrecy cloaks everything in wartime. But among shipwrights and naval engineers, one name begins to spread like quiet gospel. Tipper, December 1943, Cambridge, England. Snow drifts against the laboratory windows of Newnham College, dusting the sills white. Inside, Dr. Constance Tipper adjusts her scarf and pours a cup of tea gone cold hours ago. Her lab, a converted lecture hall filled with test rigs, fractured steel bars, and curling blueprints, hums softly with the sound of furnaces cooling. The war has aged her, though she would never admit it. There's no time for vanity when the world is fighting for survival through science and steel. She sets a new sample in the vise. This one from a damaged Liberty ship returned from Murmansk. The hull had survived being frozen in Arctic waters for weeks. When the captain sent his thanks in a letter, "Your test saved my ship, my crew, and 9,000 tons of cargo." Tipper had simply written back, "The thanks belong to the welders." But in truth, her test had changed everything. The Tipper test, now standardized across Allied shipyards, had exposed a fundamental flaw in the way modern industry viewed metal. Before, engineers believed that strength alone was what mattered. The harder, the better. Tipper proved that in the wrong temperature, strength could become the enemy. Steel needed toughness, the ability to yield and bend under stress. The British Admiralty had quietly circulated her reports to all shipyards, marking them restricted. Her name, absent from official communiqué, nonetheless traveled by word of mouth, from metallurgists to naval architects, to the men who built ships in the bitter winds of the Clyde, the Tyne, and Baltimore. One night, her assistant brings in the latest figures. Out of more than 3,000 Liberty ships now in service, only a handful have reported structural fractures, none catastrophic. Tipper removes her glasses and leans back, letting the relief sink in. 3,000 ships, she whispers. That's 3,000 chances at survival. The war presses on. The Liberty ships, once dismissed as ugly ducklings, now form the beating heart of the Allied supply chain. They carry food to Britain, tanks to Africa, troops to Normandy. Every day, a new one slips into the water somewhere. Steel plates welded, tested, and trusted. And each owes something to the quiet woman in Cambridge who refused to accept that failure was inevitable. When the SS Jeremiah O'Brien completes her 17th Atlantic crossing without incident, the ship's captain writes in his log, "The sea was cruel, the cold relentless, yet she held together like a living thing. Whoever made her bones, they understood the sea." In the years that follow, Tipper's work continues to influence how the world thinks about engineering. Her test becomes the foundation for modern fracture mechanics, shaping how aircraft, bridges, and pipelines are built long after the guns of Europe fall silent. But during the war, she remains largely anonymous, her name known only in technical circles and footnotes. When asked later if she ever felt overlooked, she smiled faintly and said, "The metal remembered me. That was enough." Outside her window, the bells of Cambridge toll midnight. Across the channel, Liberty ships plow through black waves under blackout conditions, their hulls gleaming with frost and moonlight, alive, whole, carrying the lifeblood of a world at war. They are her legacy.